Hello, this is Mr. Tala. I am here to talk to you today about a subject that is very, very complicated, and so I'm glad that you are here to hear this, because one, this means that you're here hearing this for the second time, and that's great, because this is not an easy subject. Now, to start this, let's start with a few questions that we will be able to answer by the time we are done with this lecture today. Okay. 1. Why do hot objects glow? Why is it that we see things glow red hot, like say these coils on a stove? And why does the color of the glow change predictably? Why does it go from red to yellow to white to blue? Why does it go through these different levels of color as it gets hotter and hotter? How do solar panels create electricity? Why is it that the little thing on your calculator, that little screen on your calculator, allows you to generate electricity and run your calculator from the light in the room? Why do gases glow when electric current is run through them? Why do neon lights glow when you run an electric current through them? Why would that happen? What gives fireworks their color? And also, something as simple as, what is fire, is going to be explained from this lecture. It's pretty amazing, all the things that you can explain from this, but it gets super weird and complicated, and so I'm glad you're here to hear it again. Now, something that is something where this came from, where all these ideas came from, is that elements can be identified by something called their atomic emission spectrum. So basically means that when gases are heated, they emit light. Well, first of all, white light can be split into its component wavelengths. So white light is a combination of all visible wavelengths of light. If you take this white light and you run it through a prism, like you see right here, you can split that light into its various wavelengths of light, which include everything from red to violet, which you know, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. You can split white light into all of those colors. Now, if you heat up a gas of any element, and then you shine, and then that gas glows, that light that is emitted from that gas can be sent through a prism and split into something called the emission spectrum. Because that light, when it's heated up, glows, and it emits light of certain wavelengths. And you can see right here that there are certain wavelengths being emitted by this hot gas. Okay, now the wavelengths of light that are emitted can be used to identify the element being heated, because this element of this hot gas will only emit light in these wavelengths that you see here. And so each element has its own atomic emission spectrum. As you can see right here, we can see 5 of them right here. So sodium has this particular atomic emission spectrum. And if you saw just the light being emitted by sodium, and you shine that light through a prism, and then you looked at the emission spectrum, and the emission spectrum looked like this, you could see that what that light was being emitted from was sodium. It's a pretty amazing tool to use. Hydrogen the same way. You can see it's emitting these 4 lines across its atomic emission spectrum. Calcium has its own lines, its own light signature. Magnesium has its own light signature. Neon, every element that we know of has its own light signature. Now, why do those things happen? Why does hydrogen have its specific atomic emission spectrum, and why does sodium have its specific atomic emission spectrum? Electrons can be found in orbitals around the nucleus. Okay, so you can see in this picture to the right, and you can see this picture right here, that these electrons are found in their little orbitals around the nucleus. Now, when electron has energy added to it, it can jump from its ground state, where it is when it's at rest, to something called an excited state. So let's see how this happens. Here is an atom with its orbitals, also called quantum levels. Okay. Now, it has an electron on it. It has an electron in quantum level 1. That is in its ground state. Now, when you add energy to this electron, it may jump. If you add enough energy, it may jump from its ground state to an excited state, going from quantum level 1 to quantum level 2. So, ground state is the relaxed state, the lowest allowable energy state of an atom. Atoms always like to return to their ground state, and so you will always see an atom that is not excited in its ground state. Okay? The excited state, or promoted state, is when the electrons of an atom are in a higher quantum level than the ground state. That is when the atom is in an excited state. Okay? So, again, here is ground state. You add energy to the electron, it jumps to its excited state. Now it wants to get back to its ground state, and so that electron falls back to quantum level 1, and we find it in its ground state again. Okay, now we're going to use this little step analogy right here for purposes that will be seen in just a second. But I want you to imagine that each time that the electron moves up from one quantum level to another, like it's moving up stairs, like it's moving up steps. Okay, so here it is. If we add energy to this electron will jump from one quantum level to the next. Okay, and then it will fall back down to its ground state. If we add more energy, you see it's a bigger lightning bolt, if we add more energy to that electron, it may jump from its ground level to quantum level number 3. So ground level was quantum level number 1, n equals 1. Now it's jumped up to n equals 3 because you added more energy. Okay, and then it always wants to fall back down to its ground state. All right, so a little analogy before we go any further. This little child, this adorable little child, is building a block tower. Okay, he can only add or take away height from his tower in increments of whole numbers of blocks. You can't add half a block. He doesn't have half a block. You can only add a block or take away a block. Okay, you can't add or take away a fraction of a block. Well, matter gains and loses energy in the same way. Max Planck, this guy on the bottom right-hand corner of the screen, he found that matter can gain and lose energy only in small, specific amounts called quanta. If you were talking about one of them, it's called a quantum. Okay? So if an electron is hit with a quantum of sufficient energy, it will be promoted to a higher quantum level. Okay? But if an electron does not receive enough energy to jump to the next orbital, a next quantum level, nothing happens. Also, the quanta can't build up. So, if the electron is hit with sufficient energy to jump to the next level, it jumps to the next level, and then it bounces back down. Okay? Here we see it hit with a very small amount of energy. And so, it will try to jump up to the next level, but won't make it. And it falls back down. See? Because it didn't get hit with a full quantum of energy. Now, if it gets hit with enough energy to get it to the next level, to the second quantum level, to n equals 2, but it doesn't get enough to get all the way up to the third, say this amount of energy, it will jump up. Oh, it doesn't make it to the third level, and so it falls back down to the second, and then falls back down to the first. Okay? It didn't get enough energy to jump all the way up, and so it couldn't absorb all that energy. And so it only absorbs the amount that gets it to the first level. Okay? So, this is how it works with electrons. If an electron will jump to the next orbital only when hit with light that has a frequency of 5.00 times 10 to the 18th hertz or higher. So this energy of light. You could hit that electron all day long with 4.99 times 10 to the 18th hertz, just below the hertz number of hertz that would make it jump to the next level. You could hit it with that all day long. Nothing would happen. But once you hit it with 5.00 times 10 to the 18th hertz light, the electron will jump to the next orbital. Okay? If you don't hit it with enough, you can't build up, you can't save up quanta, you can't do that. It's just not allowed. You can either, it's all or nothing. You either get there or you don't. Now, once the electrons are sent into a higher orbital, they're unstable. They're in the excited state, and they want to become stable again, back down to the ground state. And to do this, they bounce down to a lower orbital and release the same amount of energy that they absorb. So we're getting closer to the reason why they glow here. So we hit it with this energy. Jumps up to the next quantum level. When it bounces down, it releases that energy in the form of light. Okay, some wavelength of light. We hit it with more energy. Jump up to third quantum level. When it falls back down, it releases light in a stronger wavelength, in a shorter wavelength, because we added more energy, and therefore the light that is emitted will be more energetic, will have more energy. Okay. So remember that this whole analogy was based on the orbitals, the quantum levels of an atom. So let's take these steps and put them back onto the atom and look at it again. Hit this thing with some electricity. It excites the electron. It jumps to an excited state. It wants to be at the ground state, and so it falls back down to the ground state, and when it does, releases a wavelength of light. Okay? And this is why things glow. This is why gases glow. This is why hot objects glow when you heat them. This is why fire happens. Fire emits light because electrons are becoming excited, going up to excited states, and then falling back down to ground state. And as they fall down to the ground state, they release light. All right, so when matter glows, because it's hot, has electricity pass through it, is on fire, etc., it is releasing energy in particular sized packets called quanta, because those are the only ones that they can release, because they fall down from specific levels. You can measure the amount of energy in each of these quanta through this equation. The energy of a quantum equals hv. All right, the E equals the energy of the quantum. H is something called Planck's constant, which is 6.626 times 10 to the negative 34th joules. Okay? And V equals the frequency of the electromagnetic wave being emitted. Okay? So depending on what the frequency of the wave is, you can figure out how much energy is in that pocket, is in that packet of energy. Okay? Light, electromagnetic waves, travels in quanta of energy. These quanta of energy, a quantum of energy in light is called a photon, which I'm sure you've heard of before. To determine the energy of a photon in a particular frequency or wavelength of light, you use Planck's equation. Energy of a photon equals hv. All of them being the same thing, except now we're talking about a photon. So, in an example, tiny water droplets in the air disperse the white light of the sun into a rainbow. What is the energy of a photon from the violet portion of the rainbow if it has a frequency of 7.23 times 10 to the 14th hertz, or seconds to the negative 1, or 1 over seconds? Remember, H equals 6.626 times 10 to the negative 34th joules. I'll let you do the equation. Since it's E equals hv, I'm looking for E. I have H. I have V. I'll give you a second to answer that. And the answer that you should see on your calculator is this: 4.79 times 10 to the negative 19th joules. Here are a few examples. What is the energy of a photon in the following frequencies of radiation? Now, you should pause it right now, do these problems as practice. And here would be some level 4 problems. So, if I'm asking you what is the energy of a photon in the following wavelengths of radiation, you will need to use the previous equation, C equals lambda V. Because I've given you wavelength, I need you to find frequency. You need to use C equals lambda V. Figure out what V is, because you have lambda and C. And then go to our other equation, E equals HV, and figure out the energy there. So, go ahead and pause. I'll take some time to do that. Now, we're going to look at the hydrogen atom for a little bit. Here's the nucleus of a hydrogen atom. This is n equals the quantum level number. Okay, so basically the orbital. So we're going to be dealing with 7 orbitals here. Here is n equals 1. I've color-coded them so they look nice. It has nothing to do with any sort of color that's being emitted from them, but I just color-coded them so you can see. Here is n equals 2, quantum level number 2. N equals 3, quantum level number 3. 4, 5, 6, and 7. Okay, so we have 7 quantum levels, 7 orbitals. When a hydrogen atom becomes excited, it will release certain frequencies and wavelengths of light. Okay, we saw this with our atomic emission spectrum. Now we're going to figure out exactly why it releases the frequencies of light that it does. These frequencies and wavelengths are determined by the movement of electrons through different quantum levels. All right? So, when the electron jumps up to a quantum level and then jumps back down, it will release certain wavelengths of light. So let's see what wavelengths of light that a hydrogen will emit. If the electron in a hydrogen atom jumps from N2 to N1, so we add some energy, it jumps from N2, it jumps up to N2. If it falls back down to N1, it will release ultraviolet light. Okay. If it jumps from N3 to N1, so let's add some energy, make it jump from N1 to N3, now it has to fall back down to N1. It will again release another wavelength of ultraviolet light. Now, this ultraviolet light that is released is called the Lyman series. It's when electrons jump from any quantum level down to the first quantum level. Ultraviolet light is released. So you can see from 7 to 1, you would release ultraviolet light, a particular wavelength of ultraviolet light. From 6 to 1, again, ultraviolet. 5 to 1, 4 to 1, 3 to 1, 2 to 1, all are releasing ultraviolet light. Okay? If hydrogen jumps from N3 to N2, so sometimes it doesn't jump, it doesn't fall all the way down to N1. Sometimes it goes to N2 and then to N1. So, add some energy, have it jump up to N3, falls down to N2, it will actually release red light, visible red light. How about if it jumps from N4 to N2? Same process happens. We move up to N4, down to N equals 2, and it releases a teal light. If we go up to N5, and then fall down to N equals 2, releases blue light. And then if we go from N6, fall all the way down to N2, it releases violet light. These wavelengths of light that are released from hydrogen when electrons jump from any quantum level down to N equals 2 is called the Balmer series. You have purple light, violet light when electrons fall from N equals 6 to N equals 2. Blue light, teal light, and red light. So blue light when an electron falls from N equals 5 to N equals 2. Teal light when it falls from N equals 4 to N equals 2. And red light when an electron falls from N equals 3 to N equals 2. Different wavelengths of light are emitted at different because different amounts of energy are released from the electron. This is the Balmer series. And then there's the Paschen series. So sometimes the electrons jump from a quantum level to N equals 3. In this one, they release infrared light. So you can see from 7 to 3, infrared light. 6 to 3, infrared light. 5 to 3, 4 to 3, infrared light. Here is a summary of all of these, and you can see on the left-hand side we have the ultraviolet series or the Lyman series. You can see all of the arrows pointing down to the n equals 1 quantum level. You can see on the top all of the Balmer series, all the visible light series. You can see all of those arrows pointing down to the n equals 2 quantum level, because that's where the electrons are falling to. And then to the right you can see the infrared series or the Paschen series, and that is where the electrons are falling from from a quantum level down to any quantum level down to n equals 3. So, why do these things emit light? It all has to do with electrons jumping up to a quantum level and then back down to the ground state and releasing light in the process. So why do hot objects glow? Because you are heating them up to the point where their electrons are getting so excited that they jump to higher quantum levels and then jump back down and release light. How do solar panels create electricity? This actually happens in a special type of metal. It's called the photoelectric effect. But it's basically the same idea. Light hits the electrons in the metal. Those electrons become so excited that they actually fly off of the metal, then run through a wire, and that's what electricity is electrons moving through a wire. So if you can energize the electrons enough to move them through a wire, you have electricity. So that's how solar panels create it. Wavelengths of light hit the metal, excite the electrons enough to make them actually fly out of all of the quantum levels, and then off of the atom to fly through a wire. Why do gases glow when electric current is run through them? You run the electric current through them, the electrons become excited, they jump up to a higher energy level, to a higher quantum level in an excited state, then they fall back down to their ground state, and as they fall back down to their ground state, they release energy. They release wavelengths of light, specific wavelengths of light. What gives fireworks their color? Though there are different elements in fireworks that emit different wavelengths of light when they are excited, when the electrons become excited and fall back down to their ground state. And when you detonate these elements, the electrons become excited. And what is fire? Fire is just the elements that you are burning the electrons in those are becoming excited. They then jump to a higher quantum level, and then when they fall back down, they release energy in the form of light. All right, I have one last summarizing video that I want to show you of this, which summarizes basically everything that we just saw about hydrogen. So,
if a sample of hydrogen gas is heated, it gives off light. When you view this light through a prism, you'll see an emission spectrum consisting of bright lines at specific frequencies. Because the spectral lines come at definite intervals, this suggests that specific energy levels exist in the atom. A cross-section of an atom shows the energy levels similar to the rungs of a ladder. When energized, the electrons move temporarily to higher energy levels. As the electrons fall back to lower energy levels, they lose energy in the form of light, which produces the characteristic spectrum of the element. Because we know that the emission spectrum for each element is different, we also know that the distances between energy levels must be different for every element.
I hope this has helped in understanding this. And if you have any questions, you can ask me anytime. Thanks for watching.